The big mystery of physics between the mid-1700s and mid-1900s was whether light is a particle or a wave. Of course, people as far back as the ancient Greeks questioned what light was, but they could only go as far as making philosophical arguments. For example, they thought that we see things only because light starts in our eyes and travels outwards. But if that was the case, they argued that we shouldn't be able to instantaneously see distant stars when we open our eyes, unless light traveled at an infinite speed. What refutes science is better science. This finally arrived in 1800 when Thomas Young devised his infamous double slit experiment to determine the true nature of light. If you're watching this video series in order, the next few episodes really hinge on the results of Young's experiment. So now I'm going to describe to you two scenarios, one of which would show wave behavior and one which would show particle behavior. Imagine if we had a tank full of water. We're going to put in some sort of machine that bobs up and down with a gap in a wall to make sure that the only disturbance we get is from our source. Then in front of that, we have another wall with two holes in it, which I'm going to call hole number 1 and hole number 2, and then a very long distance away from that is a screen. Maybe we have some corks in the water, and we can measure the intensity of the corks as they bob up and down. So now let's look at a cork over here on the screen. If it's moving with a lot of intensity, we know that the wave that came through hole number 1 arrived at a peak, and the wave that came through hole number 2 arrived at a peak, or they might have both been troughs, as long as they're arriving in phase. Now let's pick a cork somewhere else, maybe over here. And we notice that this cork is staying at the same height. Therefore, when the wave from hole number 1 arrives as a peak, the wave from hole number 2 must be arriving at a trough, or vice versa. You might want to check out my video on wave interference, which covers this idea in more depth. So if we graphed the intensity of the wave against the various regions of our screen, the highest intensity would be in the middle, followed by regions of zero intensity, and it would alternate in this way as you looked at corks further and further out from the middle. Now let's move on and think about particle behavior. Instead of a wave machine over here, we're going to have a paintball gun, and we're going to allow this gun to shoot out paintballs in random directions, and they're allowed to bounce off the wall like this, for example. Now the reason that we're using paintballs is we can clearly see where they land on the back wall, and I think it's pretty clear that we're going to see a cluster of paintballs behind hole number 1 and a cluster of paintballs behind hole number 2, and maybe it spreads out a little bit thinner in the middle and on the outside, which is where the paintballs bounced off the wall in a weird angle, but for the most part, the paintballs are directly behind our two holes. So we have two very different outcomes, and depending on what we observe when we perform the experiment with light, we'll be able to determine whether light is a particle or a wave. When Young set up his experiment, he had to make sure that the holes themselves were very narrow. If the holes in our wall were too big, the paintballs would just get everywhere, and we wouldn't be able to determine a pattern. Or the waves would barely diffract off the boundary at all. So the slits that Young used were nanometers across. The distance between the two slits, which I'm going to call d for distance, also had to be quite small, about 0.5 millimeter. And the length L, which was the distance from the wall to the screen, was also very large in comparison to the wavelength of light. If that distance was too short, we couldn't tell if our paintballs were spreading out or clumping together, and our waves haven't traveled far enough to have a significant path difference between them. And in Young's case, even if L is 1 meter long, that should be sufficient, because the wavelength of light is only a billionth of a meter long. Finally, Young performed his experiment, and what he noticed was that the light arrived in a fringe pattern with alternating light and dark bands, and the only way that could be possible if light was able to bend around the corners and interact with itself like a wave. And so the great mystery of physics was settled for good. Case closed, no more to see here. Just kidding. What Young's discovery did was only the beginning, and it paved the way for other mysteries in quantum physics, which we will explore in upcoming videos. Let's call the fringe spacing delta x, and it could be the distance between two light bands or between two dark bands. And what Young noticed was that he could increase delta x in the following ways. He could increase the length L, he could increase the wavelength of light that he used, for example, by choosing red light instead of blue light, or he could decrease the slit separation D. So if delta x is proportional to these variables in these ways, that means that we can write this equation relating all of those variables. This has been an introduction to Young's double slit experiment. Thank you for watching, and remember to email us with your STEM-related questions or leave us a comment below.